This is video 5 in our series, Analytical Mechanics. The playlist for all the videos is featured at the website, digital-university.org. In this video, we're not going to work a Lagrangian type problem. This is going to be another illustration, though, of the technique in calculus of variations. What we have is the equation of a cone, and we want to know what is the shortest distance between 2 points on the cone. And we're going to use cylindrical coordinates when we work the problem. And in cylindrical coordinates, this is the expression for arc length, where of course r squared is x squared plus y squared. So we can say z squared equals 15 times r squared. And then z will equal 15 times the square root of r, or dz will equal the square root of 15 times dr. Now here, then for the arc length, for dz squared, we can put in 15 times dr squared. So let's put that into here, plus 15 dr squared, or the arc length would be, for this problem, it would have a general formula of dr squared plus 15 dr squared. We have 16 dr squared plus r squared d theta squared. So the arc length ds will equal the square root of this, 16 dr squared plus r squared d theta squared. And of course what we want to do is minimize the arc length, or in other words, minimize this integral, which equals, now we can factor the dr squared out of this expression. That would be equal to, this is under the square root sign now, we'd have dr squared, and then we would have 16 plus r squared. Then we'd have d theta squared divided by dr squared, or d theta divided by dr squared. And that is inside the square root sign. So for our integral, we can take this outside of the square root sign, and that would just be dr. So we'd have that ds will equal the square root and then times dr. So we're going to write it like that and make a little bit more room when we do it. So ds is equal to the integral, the square root of 16 plus r squared theta prime squared times dr, where theta prime is just d theta dr. And r, of course, is our radius, x squared plus y squared. So here, if we look at this in this kind of a format, it would be the integral of a function where the variables are r and theta prime. And we have dr, So r is the independent variable here. And in video number 3, we gave the expression for the Euler equation in various formats. One of them was if we had the integral of a function of r and theta prime, where theta prime was d theta dr, r is the independent variable, then the corresponding Euler equation was this. Well, this problem is exactly the same, except there's no theta here. So for our problem, the corresponding Euler equation is just this. This part of the problem is gone since there's no theta here for our particular integral. So here, the corresponding Euler equation is just d dr, the partial of f with respect to theta prime equals 0, where f is this function 16 plus r squared theta prime squared to the 1/2. Now, here we're saying that this derivative has to be equal to 0. So that means that what is inside of here is a constant. So we have the partial of f with respect to theta prime equals a constant then. So that its derivative is 0. So let's write it like that. We have the partial of f with respect to theta prime equals a constant. We'll call that constant k. And f is this. So obviously the next step is take the partial of this with respect to theta prime. So the partial of f, try to keep things in focus as we go along, the partial of f with respect to theta prime will equal the partial of this with respect to theta prime. So the 1/2 comes down. 1/2 16 plus r squared theta prime squared, and that's going to be to the minus 1/2 times the derivative of what's inside of this expression, the derivative of this with respect to theta prime. So here then we're going to have from, that's going to be 0 of course, then from this term we will have r squared, and here we have theta prime, so the 2 comes down, and it's 2 times theta prime. Then take the derivative of this, of course that's just d theta prime with respect to theta prime. So that's just 1. And this 1/2 and this 2 cancel. So what we have then is the partial of f with respect to theta prime will equal r squared theta prime and square root, this is a negative exponent, so that belongs in the denominator. And we have 16 plus r squared theta prime squared. That is the partial of f with respect to theta prime. And what did we say about that? It's supposed to be equal to a constant. So this is supposed to equal a constant. So here's the equation now that we have to work with. So let's make some room and write that at the top of the board and see what we can do with that. Remember, theta prime is just d theta dr. We don't want to lose track of that. Okay, let's make some room and write this at the top of the board. So we had r squared multiplied by theta prime divided by the square root of 16 plus r squared theta prime squared. This is theta, not psi. Theta prime squared equals a constant. Can we get an expression out of this for theta prime? So if we square everything, that gets rid of that square root sign. So up here we would have r to the fourth theta prime squared, and then on this side of the equation that will be k squared, and this square root sign goes away, so let's multiply both sides by 16 plus r squared theta prime squared. So we did two steps in one. We squared this equation, then brought this over to this side after we squared it. Let's bring this over to here then. We have r to the fourth times theta prime squared, and then here we have k squared r squared, so let's subtract that and bring it over to here. We have minus k squared r squared theta prime squared equals 16 times k squared. So on the left hand side we can factor out an r squared theta prime squared. We have r squared theta prime squared times, and here we'll just have r squared minus k squared equals 16 times k squared, or theta prime squared will equal 16 times k squared divided by r squared times r squared minus k squared. Or, let's see, we want an expression for theta psi, don't we? So here then we would have theta psi, or not theta psi, but theta prime, will equal plus or minus 4k divided by r times the square root of r squared minus k squared. And we're dealing with arc length, so we're just going to take the positive part of this. And theta prime is d theta dr. So we have d theta dr equals this. So we'll have to bring this over to here. And we have this expression. and we're going to have to integrate. We'll probably need some room to do that, so let's take this equation, and again, we'll put that at the top of the board and see how we're going to integrate this. But first, let's make some room. So let's see, we have d theta integral of d theta equals, and we had 4k, that's a constant, we can just take it out to here. Then we had the integral of dr divided by r squared times the square root of r squared minus k squared. Well, the left-hand side is certainly easy enough to integrate, but what about this over here? Now here we have r, of course, is one of our cylindrical coordinates. It's the radius. That's another one of the cylindrical coordinates. K was just our constant. So we have like a variable minus a constant. Usually in these types of situations is when you want to think of a trigonometric substitution. And I'm going to try this form, because you see if we had secant squared, say, of psi minus 1, that equals the tangent squared of psi. So we have a variable minus a constant. The constant is 1. So let's try this type of substitution for the r. We'll say let r be equal to, and we want to have a 1 over here eventually, so let's say r equals k times the secant of psi. Now if we do that, what is dr going to equal? So dr will equal k, and the derivative of the secant of psi, that is secant psi times the tangent of psi d psi. Now down here in the square root sign, we're going to have the square root of r squared. That's this. So we have k squared secant squared psi minus k squared, all under the same square root sign. So this, with this substitution, now becomes this. We're going to factor out the k squared, take it to the outside here. So that will be, when we take it to the outside, that will be k times the square root of secant squared psi minus 1, and that is the tangent of psi. So you have k tangent of psi. So we should have everything in place that we need to tackle this integral. So let's do that first. We have 4k, and then the integral of dr, that is this, k times secant psi tangent psi d psi, and it is divided by this, r squared. And actually that is not r squared, that is just r. If you go back, review that part of the integral where we had this down at the bottom, that was written as r, not as r squared. This is r squared. That's just r to the first power. Okay, so we have r. R is this, k secant of psi. And then we have the square root, which comes out to be equal to this, k times the tangent of psi. So these will cancel, these cancel, this cancels. So we have the integral of d psi times 4, so that's just 4 times psi. But where did psi come from? That came from this substitution right here. So we had r equals k times the secant of psi. Put this in better focus. This is just from our substitution that we did right here. So the secant of psi, that equals r divided by k. Or of course, the secant is just the reciprocal of the cosine. So if we want, we could say the cosine of psi equals k divided by r. So what is psi? Then psi, that's just the inverse cosine of k divided by r. So over here we have 4 times psi, but psi is this. So let's write that in right here. 4 times the inverse cosine of k divided by r. Okay, so this integral here is this expression, 4 times the inverse cosine of k over r, and we're going to have an arbitrary constant of integration. We'll deal with that in just a second. Let's look at this side. The integral of d theta, that's just going to be theta. So we have theta equals this integral, which comes out to be equal to this. So we have 4 times the inverse cosine of k over r. And on each side we have an arbitrary constant of integration. So let's just combine them all together into a single arbitrary constant integration. We'll have it like this. Try to keep it in better focus. Okay, remember how it was. We had this, that's just going to be theta, and this is equal to 4 inverse cosine of k over r, plus an arbitrary constant of integration, but we'll take care of that in a second. So the integral of d theta is this, so theta equals this. Then on each side we have an arbitrary constant of integration. We'll combine those into one. So there it is. If we want to, we can say, well, that would have to mean then that this will have to equal theta plus c divided by 4. And now if we want, we can take the cosine of each side of the equation, and we have k divided by r equals taking the cosine of each side of the equation. That just gives us this. On the right side, we have the cosine of theta plus c divided by 4. We can put the r over here, and we have this. So here is one of the cylindrical coordinates. It's the radius r, x squared plus y squared. Theta is the other cylindrical coordinates. This was a constant that we had gotten way back when we considered that the partial of f with respect to theta prime was equal to a constant. That's where that came from. And this was just an arbitrary constant of integration. So it looks like what we can say then is that to get the shortest distance between 2 points on a cone is that these 2 cylindrical coordinates have to satisfy that general equation. Okay, that's it for this video. In the next video, we'll try and consider some more problems, mechanical type problems, where we use the Lagrangian formulation.